this unit, we're going to continue our look at number sense. In this lesson, we're going to look at factors and multiples. Okay, hi everybody. In this lesson here, we're going to look at factors and multiples. Okay, so now, and by the way, these are words that as people go on in math, we tend to get these things confused. Okay, and so then sometimes you can be sitting in a class and your teacher, your instructor is saying something, but it's very common for people to kind of ping on the wrong thing and go in the wrong direction in their heads here. So we really want to be clear on this. Factors are often grouped as pairs and can be multiplied to get a product. Okay, so factors are the numbers that you're multiplying together to get a result, and that result is the product. So for example, factors of 24, 1 and 24, 2 times 12. Okay, 2 and 12 are the factors. 3 and 8 are the factors. 4 and 6 are the factors. Okay, so numbers that you would multiply together, and we usually write them in pairs, or you think about them in pairs, regardless, to get a different number. Now, a multiple, on the other hand, is a multiples of a number would be the row for that number in a times table. Okay, in other words, these are the values that you get when you multiply a number by something else here. So for example, the multiples of 12, well, 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36, 12 times 4 is 48, 12 times 5 is 60. These are multiples of 12. When I multiply 12 by something, this is the number that I get. So factors are numbers that multiply together to get a number, and then multiples of that number are the numbers that you get when you multiply that number by something else. So it's going to be important to keep those straight here. Now, a number can be factored. Any number can be factored or written as a product of its prime factors. So again, we're talking about factors, but now we're going to talk specifically about prime factors, where all we're using are prime numbers. And every number can be written uniquely as a product of primes. Okay? Now, prime numbers, let's make sure we're clear on this here. A prime number is a number greater than 1. It's really important. We're not including 1. It can only be divided by 1 in itself. So just as an example, 2. Okay? 3. Now, not 4, because 4, I could get 4 by multiplying 2 by 2. But 5 is a prime. There are no two numbers that multiply together to get 5 other than 5 and 1. 6 would not work, because 2 times 3 gets you 6. But 7 works. 8 doesn't. 2 times 4, okay, gets you 8. 9 doesn't work either, because 9 is 3 times 3. Neither does 10. But 11 would be a prime number, because there's no two numbers that multiply together to get 11 other than 1 and 11. 12 has got a lot of factors, but 13 is prime, and so on. Okay? Now, prime numbers are as opposed to composite numbers, are any numbers that have factors other than 1 in itself. So, for example, we could talk about 4, 6, 8, 9, 10, 12. These are the other numbers that kind of fit in and amongst there. Now, notice most of the numbers that I've written out here are even. But they don't have to be. 9 is a composite number, and it's not even. 15 would be a composite number, and it's not even. Okay? So now let's take a look at some questions that revolve around a couple of these concepts here. Okay. So our first question is, list the first 6 multiples of the given numbers. Okay. Multiples of the given numbers mean I'm going to start multiplying this number by other numbers to see what I get. And usually when we say the first 6, that's because we're going to multiply it by the numbers 1 through 6 here. So for example, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. 3 times 6 is 18. So those are my first 6 multiples of 3. 4. 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16. 4 times 5 is 20. 4 times 6 is 24. Okay, and those are your first 6 multiples of 4. Then we look at 6. 6 times 1 is 6. 6 times 2 is 12. 6 times 3 is 18. 6 times 4 is going to be 24. 6 times 5 is 30. 6 times 6 is 36. And then 12. Okay, 12 times 1 is 12. 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48. 12 times 5 is 60. And 12 times 6 is 72. Okay, and there you go. Now, the next question that says, list the factors of the following numbers, and how many factors does each one have? Now, the number of factors is going to be different from number to numbers. So, like, I couldn't just say, list the 6 factors of each of the following, because that doesn't make any sense. Okay, I can always say something like that with multiples, because I can always just choose how many multiples I want to use. There are an infinite number of multiples of each one of these things, but there's going to be a limited number of factors for each. Now, 12 could be 1 times 12, so there's 2 factors there. It could be 2 times 6. So what I'm going to do is I'm just going to increase the number here. It could be 3 times 4. Oh, and as soon as I do that, I've kind of wrapped around here. Okay, so that's 1, 2, 3, 4, 5, 6. There are 6 factors of 12. 18 could be 1 times 18. Could be 2 multiplied by 9. Could be 3 multiplied by 6. Okay, well, it's not divisible by 4, so that's kind of a dead end. It's not divisible by 5. But then I'm back up to 6. Now I'm moving back up this way. So there's going to be 6 factors of 18. 24 is 1 times 24. 2 times 12. 3 times 8. 4 times 6. Well, then I get to 5. And 24 is not a multiple. 24 is not a multiple of 5. So 5 isn't a factor. So now I've got 1, 2, 3, 4, 5, 6. I've got 8 factors. Okay. 64 is going to be 1 times 64. It's going to be 2 times 32. A 64 is not divisible by 3. Okay. It is divisible by 4, though. It's going to be 4 times 16. It's not divisible by 5. It's not divisible by 6 or 7, but it is divisible by 8. And I get 8 times 8 here. Now, you want to be careful about this one, because if you follow the pattern that I've established prior to this, you might think, well, there's 1, 2, 3, 4, 5, 6, 7, 8 factors of 64, but actually there's only 7. Because I'm just counting the numbers here as they show up here. 8 shows up twice. Okay? 8 shows up twice. And in fact, that's kind of an interesting thing. When I have an odd number of factors here, okay, an odd number of factors, it typically means that number is going to be a perfect square, something that we looked at in a previous lesson. Okay, so think about 9, for example. If I was to ask you for what are the factors of 9, that would be 1 times 9 and then 3 times 3. And so I've got 3 factors here. It's a perfect square, and I've got an odd number of factors. So now just for a moment here, we're going to take a bit of a sideways step here. We're going to look at prime factorization using factor trees. So our goal here is to break a number down into the set of prime numbers that we use to create that number. Okay? So we're going to break down the given number into 2 factors, and then we're going to continue to break down each composite factor into 2 factors until all we're left with are the prime ones. So if any of the factors are prime, we're going to circle it. And once all of the factors are completely prime, we're going to rewrite the original number as a product of those primes. Okay? And then you might want to just check to see that you've done this correctly here. So for example, for our factor tree with 100, maybe what we do is we start with 100. And I know that 100 is 50 times 2. Well, 2 is prime. So I'm done with 2 here. But 50 could be written as 25 times 2. 2 is prime. And 25 could be written as 5 times 5, and those 5s are prime. And so now when I go up here, it's 2 times 2 times 5 times 5, or 2 squared multiplied by 5 squared. That is the unique prime factorization of 100. Okay? 45, if I wanted to do that one. 45 would be 15 times 3. 3 is prime. So I'm done with that one. But then 15 is 5 times 3. And both 5 and 3 are prime. So my answer is 3 times 3 times 5. Or 3 squared times 5. And that is the unique factorization, the new prime factorization for the number 45. Okay, so now let's just do a couple questions. So this question says, determine the prime factorization of the numbers below, and we're going to write them as a product of the prime factors, then as a product of powers, which is basically what we were looking at before here. So here we go. So 24, when I look at 24, I'm going to break this into two numbers here. I might immediately see that as 2 times 12. And I know that 2 is prime. So then I'm going to focus on 12. And I know that 12 is going to be 2 times 6. And 2 again is prime. And then 6 is going to be 2 times 3. And in this case, I know that those are both primes here. So 12 is going to be 2 times 2 times 2 times 3. So that's written as a product of its primes. And now I'm going to do as powers. So this will be 2 cubed, because there's 3 2's there, multiplied by 3 to the 1. Okay, there you go. With 108, and I'm probably going to approach these in basically the same way every time I do this, just because I kind of a creature of habit here. 108 is divisible by 2. I know that it's even, so I'm going to split that up. So it'll be 2 times 54, 2 is prime. 54 is even, so I'm going to multiply that. It's going to be 2 times 27, 2 is prime. Okay, 27 is not even. So I can't divide out a 2 anymore. So there were only 2 2's in 108 here. So then I think about 27. 27 is divisible by 3. That'll be 3 times 9. 3 is prime. And then 9 is 3 times 3. So there's my last 2 primes here. So 108 is going to equal 2 times 2 times 3 times 3 times 3. And that is 2 squared multiplied by 3 cubed. And now 924. This is going to be a bigger one here. So 924, approach it the same way, is going to be 2 times 462. 2 was primed. Then I'm going to take that 462, divide by 2, and that's going to be 231. 2 is primed here. Well, now, okay, 231 is not divisible by 2. That is not an even number. So I check, okay, well, is it divisible by 3? Because 3 would be the next kind of prime up that ladder there. And yeah, it is. 3 times 77. Whoops. I'm sorry. Just instinctively wanted to circle everything there. So 77. Now, 77 is not divisible by 2. It's not divisible by 3. Now, I'm not even going to check 4, because if it's not divisible by 2, it's not divisible by 4. It's not divisible by 5. And I'm not going to check 6, because if it's not divisible by 2 or 3, it's clearly not divisible by 6. Okay, because 6 is made up of those. But it is divisible by 7. And it turns out when I do that, I get my last 2 primes out of this. So 924 is 2 times 2 times 3 times 7 times 11. Now this doesn't really simplify into a power very much. It's going to be 2 squared times 3 to the 1 times 7 to the 1 times 11 to the 1. Okay, but that is the unique factorization, prime factorization of 924. Okay, now we want to take a look at 2 ideas that are very closely related, but they are different. The greatest common factor, and then the lowest common multiple here. So one at a time here. And now that we've looked at prime factorization, what we're going to do here is we're going to use prime factorization for both of them. Okay, so now that you've got this tool, this prime factorization tool, now we're going to use it. Now, what we mean by greatest common factors, we mean the largest number that is a factor for both of those numbers that I'm giving you. Now, when the numbers are low like this, when the numbers are small, it's probably pretty easy just to list out your factors and then just look through the list and pick the largest number in both lists. Okay? That's really easy. However, it doesn't take long before it gets difficult to list all of those factors. In fact, it gets really hard. Finding the prime factorization for numbers that are quite large is still relatively quick, okay, because we do have a list of primes that we could just use to to kind of attack them. Now, when I say large, I mean as soon as you get into numbers that are up into the trillions, quadrillions, whatnot, then it gets hard here. But for relatively small numbers, the prime factorization is actually pretty quick to find. So what we want to do is I want to show you how this works. So we took 20 and we broke it into its prime factor. So 2 squared times 5. And we're using the powers there, so 5 to the 1 there. 28 is 2 squared times 7 to the 1. Now, what we're looking for are the similarities. Both of these contain 2 squared. So 2 squared is going to be, well, 4, and that's going to be our greatest common factor here. So what we do here is we take the common base with the lowest exponent. Now, so just to be clear here, let's say that instead of 20, it was 40. 40 and 28. Now, 40 would have been 2 times 20, 5 times 4, 2 times 2. Whoops, 2 times 2. So 40 would have looked like this. It would have been 2 cubed times 5, and 28 would have been 2 squared times 7. In this case, the common base is 2, but if I'm looking for and catch this, how this works here, the greatest common factor, once I've established what the common base is, I'm looking for the smallest exponent. So my greatest common factor here would be 2 squared, not 2 cubed. It would be the smaller of the two exponents. Now we're going to do an example of that in just a moment here just to illustrate that. But now, the other side of this coin here is the least common multiple. And again, we're going to use prime factorization here. But the way this one works is, remember, what we're looking for here is we're going to list off, or one way to do this, I should say, is to list off the multiples and just look for the first number that shows up in both lists. But again, that can be really difficult if the numbers are starting to get a bit bigger. Or for example, if the lowest common multiple of the two numbers isn't until they're like much bigger. So there can be a lot of space in there in between like the values as they grow up here, and it can be hard to look through those. So another way to do that is to break these apart to their prime factors again. So again, 20 and 28. Now, to get our lowest common multiple, what we do is every factor that shows up, every unique factor that shows up, okay, every unique factor gets used with its largest or highest exponent. Handwriting is awful here, but anyway. Every unique factor gets used with its largest exponent. So I have 2. Now 2 is common to both, but 2, 5, and 7. So my lowest common multiple would be 2, 5, and 7. And then we use the largest exponent. So that would be squared and then 1 and 1. So, okay, if that doesn't make sense here, let's go back to 40 and 28 again. So 40 is 2 cubed times 5. 28, actually I should do it like this, is going to be 2 squared times 7. So my least common multiple is going to be 2, okay, 5, and 7. And I'm going to use the largest exponent on both. So that's going to be 2 cubed, 5 to the 1, 7 to the 1, because 5 and 7 both only ever occur with 1. But 2 shows up twice, and I'm going to use the largest exponent. So it's going to be 8 times 5 times 7, okay? And that's actually going to get me 280. So the least common multiple here would be 280. Okay, let's take a look at a couple of examples, and that, if there's confusion here, it might help to clarify that. Okay, so here's our couple of questions here. So we're going to find the greatest common factor and least common multiple of 42 and 56. But we're going to start with finding their prime factorization. So 42, 42 is divisible by 2. That's 2 times 21 prime. 21 is 3 times 7. Ooh, I like that because immediately I got my two primes, my primes out of that. So 42 is going to equal 2 times 3 times 7. Now, 56, okay, I can break that down into 2 times 28. Okay, 2 is prime. 28 will be 2 times 14. 2 is primed. And 14 is 2 times 7. Okay, and both of those are prime. So there's my 56 is going to be 2 times 2 times 2 times 7, or 2 cubed times 7. Okay, so my greatest common factor is going to use just the factors that are common to both. Well, there's a 2 common to both, and there's a 7 common to both. 3 isn't. 3 is unique to 42, so I'm not going to worry about that. I'm only looking for what's common. But because I'm looking for the greatest common factor, I'm going to use the smallest exponent. So in 42, it's 2 to the 1. In 56, it's 2 cubed. So the smallest exponent is 1. And with 7, it's 1 in both cases here. So my greatest common factor is going to be 2 to the 1 times 7 to the 1, or just 14. Now, my least common multiple uses all unique factors. So I've got a 2, I've got a 3, and I've got a 7. I don't care if it's common. I'm just looking for the unique factors. Now, and because I'm looking for the lowest common multiple, I'm going to use the largest exponent that I see. So between the two different 2's here, there's 2 to the 1 and 2 cubed, I'm going to use cubed. Well, there is only a 3 to the 1 and there is only a 7 to the 1. So that's as far as that would go here. So then this becomes 2 cubed times 3 times 7, and we get that the least common multiple of those two values is going to be 168. So in other words, if I was to list off all of the multiples of 42 and 56, I wouldn't see overlap until 168. Okay, let's do it again. So 180. Now I'm gonna do this in a slightly different way. I'm going to do this for both of these numbers here. 180 is clearly the same as 10 times 18, or 18 times 10. 18 is 2 times 9, so 2 is prime here. 10 is 2 times 5. And actually, those are both prime factors. So 2 rows down, I've got 3 prime factors here. And then 9 is 3 times 3. And so those are all my factors. Nothing else can be broken down. So 180 is going to equal 2 times 2 times 3 times 3 times 5. So in other words, 2 squared times 3 squared times 5 to the 1. 420, well, I'm going to do the same thing. 420 is the same as 42 times 10. Okay, 42 is 6 times 7. 7 is prime. 10 is 2 times 5. Well, both of those are prime. The only one I have left is the 6, and that's going to be 2 times 3. And so then those are prime. So now I've got these prime numbers as well here. So 420, I'm going to lose it there, is going to be 2 times 2 times 3 times 5 times 7, or 2 squared times 3 to the 1 times 5 to the 1 times 7 to the 1. Okay, so my greatest common factor is going to be equal to just a number that has just the list of common factors, common bases, which will be 2, 3, and 5. 7 is not common to both. And then for the greatest common factor, I use the smallest common exponent, or the smallest exponent that shows up. So between the two numbers here for 2, it's squared. Then I've got 3 squared and 3 to the 1. So in this case, it's going to be 3 to the 1. In this case, I've got 5 to the 1, 5 to the 1, so it's just going to be 5 to the 1. And so altogether, that's going to end up being 60. My least common multiple uses all of the unique factors, so 2 times 3 times 5 times 7. And again, when I say unique factors, what I mean by that is just all the different numbers that show up. I don't care if they're shared by both of them, just if it shows up, I'm going to list it down here. But now I'm going to use the largest exponent, so between the 2's, it's still going to be just a squared. But for the 3, 2 is the largest, okay, the largest exponent on there. And then for both the 5 and the 7, it's just going to be the 1. So that's going to be, when I multiply those all out, that gets me 1,260 would be my least common multiple. So you're going to have to go a little ways out before you can figure out what number is common to both their lists of multiples.